first presenter for today is Dr. Glenn Washer. Dr. Washer is a professor at the University of Missouri in Columbia. His research interests are focused on condition assessment technology for civil infrastructure. This includes developing non-destructive evaluation technologies for damage detection, reliability of inspection technologies, and risk-based inspection. The results of his research include the new AASHTO manual for bridge element inspection, approved in 2018, and recent changes to the NBIS to allow risk-based inspection. Please welcome Dr. Washer.
This is work related to NCHRP program that happened a few years ago, and we'll talk a little bit about the goals and objectives of that research, the outcome, and this presentation is really about the quality of element level inspections. We did some testing in the field that looked at the variation, and quality is kind of another word for variation, right? How much does the results that you get out of the inspection vary from the intended answer or the mean or some other measurement of what the variation of it is as a means of assessing what the quality of that inspection and what the quality of the data that is the outcome of the inspection is. And so we'll talk about that, sort of put this in this order, that first some field exercise results for element level inspections of different elements, and then some improvements to the MBI that resulted from those, which you've probably been familiar with because that book's been out for a few years now. But if you ever asked, wondered, well, why was this book changed, or what was behind the reorganization of this book and the addition of all these pictures, well, this is the research that went into that. And so the goal of the project overall was to improve the quality of element level bridge inspection data and develop some guidelines to do that. I think that in the reports there is information about quality programs, which I'll mention in here, and a big part of the program ended up being to update the manual for bridge element inspection to improve consistency in the data collection by better defining the condition states through the use of photographs and visual aids. We also did some work on establishing accuracy levels for element conditions and defect quantities, and how that would affect your bridge management program. And so that's not in this presentation today, but if you were interested in that, you could look in the report. We did some sort of hypotheticals. If you were doing, for example, Markov modeling for deterioration, how would this error going in affect the outcome of that Markov model? And so, like I said, that's not in my presentation today, but you could look in the report and see that. And so I thought would be interesting today is to look at the field trials that were done as part of that research, and what the outcome was in terms of variation in the inspection data from a group of inspectors in 2 states. And so the objectives of this overall were to sort of test drive some visual standards we were coming up with at the time, pictures of different element states. And so you'll see in these results there's a test group A and a test group B. Some are using photographs, others are using just a conventional condition descriptions. We didn't find a lot of difference in that in the field testing that we did. We think partially because they'd only been just introduced to the pictures. It was probably not a good way to test that. And so we really looked at this as largely the results I'll talk about is just combining these 2 groups together and to look at the variation of their assessment of element level conditions, and largely in terms of quantity, but a little bit in terms of what the condition state is. We looked at the accuracy of the inspection, timeliness, how long does it take to do these different things, and assess potential changes to the MBEI. So what I'll talk about in this presentation is some of the results from what the inspectors saw when they went to the field. And the idea here is that we take a group of inspectors, 10, 14 inspectors, I think it was 10 in one state and 14 in another, and we take them and we have them do an inspection, the same inspection of the same bridge, so everyone's looking at the same thing, but independently, and then compare their results one to another. And the other thing we did in this study was we found bridges that were sort of sister bridges, so they're next to each other, they have exactly the same design, built at the same time, and they have similar conditions, and so you get sort of getting some repetition in that test set and see if the results are particular to a particular bridge or are they uniform across different bridges. And so we did pre-stressed bridges in Michigan, along with decks, and then steel bridges in Indiana. And just for some logistical issues, the decks in Michigan were actually not on the same bridges that we did the superstructure and substructure for. We did the decks separately. In Indiana, we did the bridge with superstructure, substructure, and deck. And what I'll talk about today here is just the element level inspection results. And so these things are measured in terms of quantity and condition state, as compared to the NBI condition rating scale, which is a 0 to 9 scale that gives you a rating as compared to its original design condition. And some measurement of safety. In the element level, you really have just these quantities and general condition states. And so there's a little different animal in terms of what you get out of it. We had about 10 inspectors. It was 14 in one state and 10 in the other. Go out and look at these sister bridges. We did a bunch of research on inspector characteristics, how are they educated, things like that. I don't have that today, but there is a report online that you can find on that research that if you were interested in that kind of area. Now, we did some of this testing at the Esbright Center at Purdue. If you're not familiar with that, I do a lot of work with Rob Connor from Purdue, and he's been collecting up old bridge parts over there, and he does some training on fracture critical inspection and bolt installation as well for some states that are partners. Some folks in the Northeast might be partners in that. It's a pooled fund. So he and I work together on a lot of different projects having to do with inspection. Big thing we're doing right now is working on the T1 steel issue, working with some federal highways to clarify some questions about how you might do that inspection, but also to work on the ultrasonic testing and performance testing of inspectors. And it's a similar related thing in that, you know, just like with visual inspection, you get this lot of variation between inspectors. For ultrasonic inspection, particularly if you're using it in the field the way it's going to be done on T1 steels, or is being done, there's a lot of variation between inspectors. And so we've done result test on that in the past. There is, if you're interested in this issue, touch base with me because we can talk some about what we have done and what we're doing currently. I was just actually earlier this week in Iowa working on a bridge to look at how you can find welds in these T1 steel when it's not at a transition and maybe not in the plans, using an NDE technology so you can locate a weld, for example, that was used to extend the length of a plate. And the old, when the T1 steels, which are quench and tempered steels, a lot of them were originally built, the ovens for doing the tempering were not very large. And so if you had a plate in excess of 50 feet in length, you had to weld together two plates. And so you've got some weld in these plates that you probably can't find. And so we're doing sort of work in that area. And so if you have questions about that or interested in that, touch base with me after we talk a little bit about the T1 steel efforts. So we collected up a bunch of these steel parts over at Purdue. We've got a part of the campus there that's dedicated to it. And so we use that as a test site to be able to take inspectors there that were from Indiana and run some tests in a controlled, sort of more like a laboratory environment. One of the things we did was we put a bunch of white appliques on the side of a plate girder bridge, right, to say, okay, if this was the corrosion damage in this bridge, how do you estimate what the areas are? And we looked at a couple things, you know, and if you think about, I don't know, you know, some of you may be involved in element level inspection, some of you not, but, you know, if the inspector reports, for example, that this 10% of the bridge deck is deteriorated, well, how does he determine it's 10%? Does he do it by just looking at it and making a general assessment, well, it's about 10%, or does he find all the areas where there's damage and tally them up, and do those give the same results? That was one of the questions we wanted to check in this testing at Purdue, and so we looked at that. I'll show some results here. And this slide tells a little bit about, right, that one inspector might go out, and we asked the inspector, we got a wide variety of results. You know, do you tally up each individual area that you see that's damaged, or do you just look at it and make a general assessment of what the percentage is? And so we had inspectors that did both. We had one inspector that said, well, I tally up all the areas and then I multiply it by some other number that he had invented it, because he found from his experience that the actual defects were 20% more than what he could see or something like that. So there's a wide variety of the way, right? He was the only one that did it that way. It was a secret formula. And so the wide variety of how this thing is done. But we had this this plate girder bridge, this one on the top here, the blue, with some white appliques on it. We said, okay, just go through and we want you to estimate what the area is just by looking at it and give us an estimate of the area. And then we rearranged the white appliques because we could take them off and make them different. They said, okay, now go through and tally them all and tell us how much it is and what are the results. And so the results kind of look like this. On the left here is the tallying results where they went through and they tallied up all the areas. On the right is when they just estimated the percentage of the areas, okay? And so this was done, and what you see here is a couple things. One is that when they tallied the areas, they overestimated in almost all the cases. The triangles on here, the gold triangles, are the actual numbers, okay? What it actually is. And the tallying always overestimated it, whereas the if you looked at the percentage of area, you got more of a above and below sort of thing here. I've got some fancy stuff on my slides I forgot about. The arrows don't come up. You get both, on average, it's close to the right result, but the spread is greater, right? And so that's kind of interesting. So some people underestimate it, some people overestimate it. The average of those comes out pretty close to the right answer, whereas if you're tallying, you're usually overestimating. We also did this for lengths, for things that were like a girder where you do linear feet of length. Similar results, right? You get Tallying usually overestimates the amount. Just guessing at the percentage gives you a little bit closer estimate, I guess, or closer average, because you get both above and below. Now, the other thing about this is if you look at here, there's time shown in this graph on the right, it's around 5 times as much time to tally it as it does to just write a percentage estimate. And so the time required is a lot more significant for that. And so the percentage estimate has, some advantages, but if you look at the spread of it, we looked at the damage percentage on these and we got answers from inspectors. Each of those little blocks is an answer from an inspector, right? So one inspector said, well, it's about 70%, and another inspector said, well, it's about 10%. And so that's about as much variation as you could possibly have, right? And so how do we go after this? One way we went after this is in the new manual for bridge element inspection, and I'll show this later if I have time, that there is a portion where you can look at some pictures and say, well, this is what 10% looks like of an area, okay? And it's just a plan view drawing with sort of this defect drawn on there. This is a defect that's 10% when it's in one spot. Here's 10% when it's in lots of different spots, etc., things like that. We had them do a section of a truss that was there. There's a truss with no deck on it. You see the results over here. And the way these results are presented on some of these conditions in the field is what they said is that, in this case, linear feet of length in condition state 2. What did they say was in condition state 3? And if you considered, let's just look at how much damage they reported, so we'll combine condition state 2 and 3 together. And so you sort of see that, well, in terms of the amount of damage, there's some consistency. I mean, one inspector sort of out on his own here, but in total damage, but the spread in whether it was condition state 2 or condition state 3 is huge, right? And so that shows that there's not a consistent understanding of what is condition state 2 and what should be rated as condition state 3. We did other stuff that was in the field, on actual bridges in the field, a couple of bridges on I-65, right, in the West Lafayette area, actually. And here you see spread of results, like, for example, the steel girder element for corrosion damage. So again, this is condition state 2 results. We get results somewhere from 0 up to 600 square feet. Condition state 3 results here somewhere close to 0 up to 300 linear feet, rather, excuse me. If you looked at condition state 2 and 3 together, just adding them together, you get that kind of spread there. And so this is 2 bridges that are side by side. They're in different conditions, but their construction is exactly the same, but the results are pretty consistent just to look at it graphically, right? It didn't matter the bridge on the left or the bridge on the right. The spread was pretty similar. The important stuff is kind of over here, and here is, there's, as I said, we had 2 teams, but if you look at this combined result column, I think is the most important one. You see what the mean is for the condition state 2, condition state 3, and again, what if we just look at this, how much damage did they report, whether condition state 2 or 3, right? The mean was about 32. The standard deviation is about 30, so that this coefficient of variation, this is just the ratio of the standard deviation to the total amount. So it's about 94%, right? And so it's sort of close to plus or minus 100%. That was pretty consistent result. I think what we came up with ultimately in the conclusion, when I get to the conclusion slide, is the results vary by plus or minus 50% on the low side, and often they're very much higher. And so here's a pre-stressed girder. This is looking at a situation, well, what if there's very little damage? Pre-stressed girder didn't have much damage in it. Again, these coefficient of variations, which tell you the percentage of spread as a result, as a portion of the mean value, are up around 100% in some cases, right? 80, 90, 100%. So there's a lot of variation, and that is the outcome point of that. We also looked at some other things that were a little more specific in terms of what people might be interested in for the element manual. We looked at what is the difference for columns that are currently rated as each. What if you rated them as linear foot? One of the things you get when you rate it as linear feet is a lot less damage. And so if you want to improve the condition of the bridges across your state, you should go take your columns from each to linear feet, because then you'd have a lot less damage. I'm not exactly sure why columns are rated as each and not linear feet, but I do know that every conversation I've ever had about it was at least an hour long, and whoever I was talking to was totally committed to whatever unit they were currently using. And they couldn't believe someone would use any other unit. Similar results for deck results. There's information for bridge decks, a similar sort of thing, and you can look in the reports online. This was the bridge deck with the most damage out of the ones we looked at. You see a mean value here is around 8% in condition state 2 and 3% in condition state 3. The average for the combined damage 2 and 3, just if you look at how much damage did inspectors report, it's about 9%. And the coefficients of variation here, again, 60%. And so that means if it was, if the inspectors on mean had said it was 100 square feet, the actual answer was somewhere between 50 and 150, right? That's essentially what that's what a 50% COV means. And it would be 68% of the answers would go in there statistically. So that's kind of an important value. But the overall theme is, well, there's a lot of variation when humans go out and look at things. And so the other result, just quickly here, is another issue that we have for element level inspections. The more damage you have, and we consistently found the more variation you have. And so it sort of gets worse as the bridge gets in worse condition in terms of the spread of how much, what the spread is of the actual quantities reported. On the good side, we did find that for condition state 3, and this graph on the right, sort of a lot to take in, but what it says basically is that the rate at which someone would report a condition state 3 goes up as the amount of condition state 3 goes up, which is good, right? If you got on average 30% condition state 3, the likelihood the inspector is going to make some sort of a report of condition state 3 is increased as compared to if it was, say, 10%. Okay, and so that's kind of a good thing. So the conclusion from the field trials was that the variations, at least plus or minus 50%, looking at different inspectors, looking at exactly the same damage. Some other things we found, we looked at gusset plates. What's the chances some inspectors going to rate that gusset plate as condition state 4, which would be an important and critical sort of finding. That had a lot of variation in it as well. So what do we do about all this change? Well, a lot of the changes in the Manual for Bridge Element Inspection sort of came off of this research and other stuff that's been done over the years. What can you do? Well, you can improve quality control and quality assurance programs. And the second thing is improved resources for inspectors. And so the revisions for the Manual for Bridge Element Inspections, a lot of them are pointed at improving the resources available for inspectors. In terms of QA programs, there's a little known report that the T18 committee did that I wrote for the T18 committee back in 2009 on quality assurance programs in the US, how different states did them. Sort of define these as 4 different possible models: a collaborative peer review model where a group goes out and looks at a bridge and discusses what its condition is, an independent oversight model, which is what they use in Pennsylvania, or at least they used to use, I think they still do, where you hire a contractor to come in and re-inspect some bridges and check against what the original inspection did and see how much variation there is. A control bridge model, which is used by more states over time. Oklahoma sort of started this, where all your inspectors go and look at the same bridge and then you score them relative to each other as compared to an expert panel. So those are quality programs, and this report's on the web. If you're interested in that, you can go through and look at it. One of the ideas that we want to do as well, there's an inspector calibration needed to try to get everyone singing from the same hymnal, so to speak, get them to all report things the same. That's using these quality assurance programs. They can be contributing to that. Visual guides is another way to do that. And so what we did in the update to the manual was to provide visual guides for all the condition states. So you can look at that, and here's what a picture of condition state 2 looks like. Here's what a picture of condition state 3 looks like. And I'm short on time, so I'm just going to skip ahead a little bit. So we rearranged the manual to be listed by material that cut a lot of the repetition in the manual, make it simpler to use. And we added these photographic images that tell you what the different condition states should look like, okay? And one of the neat things, I think, is that we also put in boundary images that show what does it look like between, say, condition state 2 and condition state 3. So that gives an inspector a chance to sort of look at that. And again, it's not going to be a perfect comparison, but say, okay, if I've got more than this, it should be 3. If I've got less than this, it should be 2. And so that kind of gives you a boundary line. It's not appropriate for all elements, but where it was, we tried to put those in. And so when you look at the manual now, you see these pages that look like this. They've got these visual guides that show different types of damage on it. We also added some things to try to help people make spatial estimates, and we're able to sneak in a couple of MU logos along the way as well. So if you look at the manual, there's a picture of one of my credit cards. Shows you what the thickness of a card is, what the tip of a pencil is, so if you want to estimate crack width, for example. So these are all tools for inspectors to use to try to improve the quality of element level inspection. Doing all this cut down the size of the manual pretty significantly, and if you've got the new version, you've probably realized that. It was a 269, we got it down to about 149, even less after we made some additional configurations, so you can print it and bring it to the field with you and have that right in there. So that's my presentation, Rich. I hope, I still got 5 minutes, good. I wanted to have a couple minutes for questions. So just in conclusion, our field trials illustrate a lot of variation, and that's another way to say it's sort of low quality, right? The variation is high. That means the quality is sort of low. So how do you address that? Quality assurance programs can be used to do that, and there's some training and involved in that, and there's different models. I refer you to my report from 2009 if you want to learn something about what those models are. Some states are using performance testing type of inspector qualification. Others are using different models. So might be interesting. Then we modified the manual for bridge element inspection. That was accepted in July 2018. We've been adding some other elements over time. I think at the AASHTO meeting next week, we'll be talking about a standardized methodology for adding or changing elements that are in the manual that'll make it more systematic going forward, so it'll be more like other specifications. There's a final report. It's a web-only document. And in terms of future implementation, calibration exercises and training are something that we try to encourage people to use to try to improve the quality of their element level inspections. So, and that's it. I'm happy to answer any questions if anybody's got any.
When the new element level stuff came out, we were very concerned on the time that it was going to add to our inspections. We always did some type of element level inspections from the beginning of it. Do you have any guidance for us that we could use? Because all the data is great, but we don't have the resources. You know, we have X many bridges and not enough inspectors and not enough time to do it, but we have to get it done or Federal Highway is going to kick us in the butt.
Yeah.
Do you have any guidance that might be able to help us that way?
Well, you save time if you use a percentage estimates. That's one way, as opposed to tallying the estimates. But other than that, not a lot, because the sort of rule for visual inspection, and this is in a lot of research, that there's a time accuracy relationship, and so the quicker you do it, the lower your accuracy is. And so as you try to rush it, it becomes less accurate. So, that's sort of doing the tallies. Like in Missouri, we only do the state bridges for one reason. I think that's all that's required right now. Training people to do percentage estimates, can cut the time if they're doing tallying. If they're not doing tallying, then that's obviously not going to save you any time already. And using the visual guides. But yeah, it's definitely going to take more time to do, to do the tallying, to do the recording of all that element level. So, yeah, that's I don't have a lot other than that. Yeah, it takes more time to do element levels, surely. Yeah, and I don't think it'll ever go back to just one or the other. I think it'll always be both. Because
I like both.
I do too. Yeah, because the NBI rating has a safety element in it, and the elements really have most of the management. It doesn't tell you whether it's important or not. And you can have 10% delaminations, but if they're all in one spot on the bridge, that's a lot worse condition than if they're, spread all over the bridge. So, did someone else have a question? Yeah.
I was just going to make a comment, and that we kind of, in North Dakota, we kind of used Federal Highway as the bad guy, and they made us. They really pushed at PCAs and various things, and so we were able eventually to make some changes and to get some things done. But yeah, use Federal Highway if you can as the hammer.
We don't have a solution. We don't have a solution, but we have someone to blame. So there you go. Thank you. I'll see you in a minute.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.